Before going any further, one thing needs to be clear. Voyager 1 is not receiving a message from anyone. It's not picking up an alien transmission. What it actually detected is, in some ways, even stranger, a faint, constant, unbroken hum coming from the empty seeming space between the stars, a sound scientists didn't even know existed until Voyager accidentally stumbled onto it. Stick around, because I'm about to walk you through exactly what Voyager 1 picked up, why it took researchers years to even notice it was there, and what this discovery is now teaching scientists about a part of the galaxy no human instrument had ever measured continuously before. And hit subscribe now, because this channel breaks down real space discoveries without the exaggeration, and this particular signal has been running quietly for years, without most people ever hearing about it. Let's start with where Voyager 1 actually is, because the location matters enormously for understanding what it's picking up. Launched in September 1977, Voyager 1 spent its first years touring Jupiter and Saturn before continuing outward, eventually crossing the Heliopause in August 2012, the boundary, where our sun's constant outward stream of charged particles finally gives way to the material drifting between the stars. That crossing made Voyager 1 the first human-made object in history to leave the protective bubble our sun creates around the solar system. Today, the spacecraft sits more than 14 billion miles from Earth, traveling at roughly 38,000 miles per hour, the most distant object humanity has ever built. Confirming that 2012 crossing at the time wasn't simple either, which is worth understanding since it connects directly to this later discovery. Voyager 1's dedicated plasma science instrument, the equipment specifically built to measure the density and temperature of surrounding plasma directly, had stopped working back in 1980, shortly after the spacecraft's Saturn flyby. Without it, researchers had to rely on a separate instrument, the same plasma wave system that would later reveal the hum using a solar eruption shockwave to indirectly calculate plasma density and confirm the spacecraft had genuinely crossed into interstellar space. That confirmation didn't even arrive until more than a year after the actual crossing had happened, once a fortunate solar event in April 2013 finally provided the missing data needed to settle the question. If you're the kind of person who wants space discoveries explained clearly instead of buried, in jargon, go ahead and drop a like on this video right now, because it genuinely helps this kind of content reach more people who would enjoy it. Here's what most people don't realize about interstellar space. It isn't a true, perfect vacuum. It's filled with an extremely thin, mostly invisible material called the interstellar medium, made up of ionized gas, or plasma, along with energetic particles and faint traces of matter left over from stars that lived and died long before our own sun ever formed. It's about as close to nothing as anything gets, but it isn't literally nothing, and Voyager 1 carries an instrument specifically capable of detecting it, called the plasma wave system. To put just how thin this material actually is into perspective, the interstellar medium immediately surrounding Voyager 1 contains roughly 1 electron per every 10 cubic centimeters of space, an almost incomprehensibly sparse density compared to the air filling the room around you right now. And yet, sparse as it is, this thin scattering of charged particles still behaves according to consistent, measurable physics, still responds to disturbances by vibrating at specific frequencies, and still, it turns out, produces a signal steady enough for a sufficiently sensitive instrument to detect continuously, even without any dramatic outside event triggering it. For years after crossing the Heliopause, the only way researchers could actually measure the density of that surrounding interstellar plasma was to wait for a specific, fairly rare kind of event. Occasionally, a powerful eruption on the sun, a coronal mass ejection, sends a shockwave rippling outward through the solar system and beyond. When that shockwave eventually reaches Voyager 1, even out in interstellar space, it sets the surrounding plasma vibrating, and the plasma wave system can pick up those vibrations clearly. By measuring the specific frequency of that vibration, scientists could calculate the plasma's density using established physics. This is actually the exact same method researchers used back in 2013 to first confirm Voyager 1 had genuinely crossed into interstellar space at all, after a solar eruption from earlier in the year finally provided a clear enough signal to settle the question. Relying entirely on these shockwave events created a genuine scientific bottleneck. Coronal mass ejections powerful enough to still produce a detectable shockwave after traveling 14 billion miles don't happen on any predictable schedule, and the sun can go through extended stretches of relatively low activity where strong enough eruptions simply aren't occurring at all. That left researchers with only occasional unevenly spaced snapshots of the interstellar plasma's density, rather than anything resembling a continuous, reliable dataset. Between those infrequent events, the assumption had always been that Voyager 1's instruments simply had nothing meaningful left to detect, that the intervals separating one solar shockwave from the next were essentially dead time as far as plasma density measurements were concerned. If you found this as fascinating as I did while researching it, drop a comment letting me know. because it genuinely helps me figure out what other space stories are worth covering next. But solar eruptions powerful enough to send a detectable shockwave all the way out too. Voyager 1 don't happen constantly, and between those events, researchers assumed interstellar space would sit essentially silent as far as their instruments were concerned. That assumption turned out to be wrong. The team led by Stella Koch-Ocker, a doctoral student in astronomy at Cornell University, went back through Voyager 1's data looking, specifically at the quiet stretches, the periods between solar shockwave events, expecting to find nothing meaningful there at all. Instead, they found a signal, faint, narrow, and remarkably steady, a persistent low-level hum coming from the plasma surrounding the spacecraft, present continuously, not just during dramatic solar outbursts. Ocker described the finding plainly, saying the team was detecting the faint, persistent hum of interstellar gas, adding that it was very faint and monotone, sitting in an extremely narrow frequency bandwidth. James Cordes, a Cornell astronomy professor and senior author on the study, offered a memorable way to picture the difference between the two kinds of signals Voyager 1 could now detect. He compared the newly discovered constant hum to a quiet, gentle rain, while describing the dramatic solar shockwave events as more like a sudden burst of thunder cutting briefly through that steady background rainfall, before everything settled back into the same faint, continuous drone. The research team published their findings in the journal Nature Astronomy on May 10, 2021, under the title Persistent Plasma Waves in Interstellar Space Detected by Voyager 1. What makes this hum genuinely different from the previously known shockwave signals isn't just that it's fainter. According to the paper, this new signature is distinct from the shock-generated plasma oscillation events specifically because of its narrow bandwidth, low amplitude, and multi-year persistence, meaning it isn't a one-time event at all, but an ongoing, continuous feature of the interstellar environment. Voyager 1 has simply been sitting inside the entire time. Here's why this discovery actually matters, beyond just being an interesting curiosity. Before finding this constant hum, researchers had no reliable way to track the density of the interstellar medium except by waiting for the sun to cooperate with a strong enough eruption. Shami Chatterjee, a Cornell researcher and co-author on the study, explained the significance directly, saying the team had never previously had a chance to continuously evaluate the density of interstellar space, and that discovering this persistent hum meant they no longer needed a fortuitous, unpredictable solar event just to take that measurement. In other words, Voyager 1 had accidentally handed scientists a continuous, ongoing measuring tool for a region of space no human instrument had ever been able to monitor this consistently before. That capability turns out to be genuinely valuable for a specific reason. Astronomers already had a general sense that plasma density in the interstellar medium should gradually increase the farther a spacecraft travels from the heliopause based on existing theoretical models. But confirming that gradual increase with real, continuous data, rather than a handful of scattered measurements taken only whenever a solar shockwave happened to pass through, gives researchers a genuinely reliable way to test and refine those models against actual, ongoing observations. Ocker has said she believes there's considerably more low-level activity happening in the interstellar medium than scientists previously assumed. Activity. This persistent hum finally gives researchers a consistent tool to actually study in detail. It's worth explaining a little more about what's physically producing this sound, since interstellar space doesn't behave the same way air does here on Earth. Plasma is essentially a gas made up of charged particles, electrons and ions, rather than the neutral atoms that make up the air we breathe. When something disturbs that plasma, whether it's a distant solar eruption, energetic cosmic rays passing through, or simply the ambient thermal motion of the particles themselves, the electrons within it begin oscillating at specific frequencies, tied directly to how dense the surrounding plasma actually is. Voyager 1's plasma wave system doesn't work like a traditional microphone, picking up actual sound waves, since sound as we experience it on Earth requires a medium far denser than the near vacuum of interstellar space to travel through at all. Instead, the instrument detects these electron oscillations directly as electromagnetic signals, which scientists back on Earth can then convert into audible frequencies, translating an invisible physical process into something the human ear can actually recognize as a tone. This isn't a phenomenon unique to Voyager 1 either. Voyager 2, which crossed its own section of the Heliopause in November 2018, 6 years after its twin and heading in a completely different direction through the sky, carries a very similar plasma wave instrument, and researchers have continued monitoring its data for the same kind of persistent signal. Finding a comparable hum in data gathered by a second spacecraft, traveling through an entirely different region of interstellar space, would give researchers valuable independent confirmation that this isn't some strange artifact specific to Voyager 1's particular flight path or instrument calibration. but a genuine widespread feature of the interstellar medium itself, present in multiple directions, away from our solar system rather than isolated to just one narrow slice of the surrounding galaxy. That translated sound has an eerie, genuinely otherworldly quality to it, a thin, steady, almost musical drone, utterly unlike anything most people associate with the idea of empty space. It's not something Voyager 1's instruments were originally designed specifically to capture. This entire discovery came from researchers carefully combing us back through years of accumulated data originally gathered for other scientific purposes, and noticing a subtle, consistent pattern sitting quietly in the background the whole time, waiting for someone to actually look closely enough to notice it. There's something genuinely fitting about where this discovery came from, too. Voyager 1 launched carrying a golden record, a message from humanity assembled under the direction of the late Cornell astronomer Carl Sagan, containing greetings, music, and sounds meant to represent life on Earth, intended for any future finder who might one day encounter the spacecraft drifting through the galaxy. Decades later, a team of researchers working at the very same university where Sagan once taught used that same spacecraft to capture humanity's first continuous recording of what the galaxy itself sounds like, an unplanned, almost poetic bookend to the original mission Sagan helped design nearly half a century earlier. A disc containing greetings in dozens of languages, music spanning different cultures and eras, and natural sounds like wind, thunder, and birdsong, all etched into its explaining how it might be played back. Sagan and his team assembled it in 1977, fully aware that the odds of it ever actually being found and understood by another civilization were vanishingly small, but treating the attempt itself as worthwhile regardless. There's a certain symmetry in the fact that the same spacecraft carrying humanity's outbound message ended up decades later sending back an entirely different kind of message of its own, not one deliberately encoded for anyone to find, but a genuine, natural signal revealing something true about the actual physical nature of the space between the stars. Ocker herself captured the broader significance of the moment well, describing Voyager 1 as a testament to just how much value can still be extracted from remarkably old engineering, calling the spacecraft the engineering gift to science that keeps on giving. That description holds up. Voyager 1's instruments were built using technology from the 1970s, designed originally for a mission expected to last only about 4 years, focused on studying Jupiter and Saturn up close. Instead, nearly 5 decades later, this same aging hardware is still returning. Genuinely novel scientific discoveries revealing details about the wider galaxy that no other instrument humanity has ever built has been positioned to measure. That's a genuinely remarkable outcome for a piece of equipment built decades before most of the researchers currently studying its data were even born. The plasma wave system itself wasn't specifically designed with this kind of persistent, low-level hum in mind. It was built to characterize plasma conditions during Voyager's original planetary flybys and to catch the occasional dramatic shockwave event as a secondary capability. That an instrument engineered for one specific purpose, using electronics that would look almost primitive by today's standards, turned out to be sensitive enough to catch a signal this faint, this many decades after launch, says as much about the quality of the original engineering as it does about the persistence of the researchers, who kept combing back through the data long after most people assumed there was nothing left to find in it. It's also worth being clear about what this discovery does not represent, given how easily a phrase like signals from deep space can get twisted into something it isn't. This is not communication. It is not evidence of anything artificial, intelligent, or directed. It is the natural, physical behavior of ionized gas reacting to its environment. A genuine, measurable phenomenon researchers can study using established physics, not a mystery pointing toward anything beyond ordinary plasma dynamics. What makes it remarkable isn't any hint of alien contact. It's that humanity now has a working, continuous window into the actual physical conditions of the space between the stars, gathered by a machine built before most of the researchers studying the data today were even born. So what does all of this actually add up to? A spacecraft designed nearly 50 years ago, using an instrument built to catch violent, occasional bursts of solar activity, ended up detecting something nobody was specifically looking for. A faint, steady, continuous hum, running quietly beneath those bigger events the entire time. That discovery gave scientists their first reliable, ongoing tool for studying the density and behavior of interstellar plasma without needing to wait for the sun to cooperate, opening up a genuinely new way to study a region of the galaxy that, until Voyager 1 got there, had never been measured this closely by anything humanity had ever built. There's a broader lesson here too, one that applies well beyond this single discovery. Some of the most interesting findings in modern astronomy haven't come from building an entirely new instrument specifically designed to detect one particular phenomenon. They've come from researchers returning to data already sitting in an archive, sometimes years or even decades old, and simply looking at it more carefully or asking a slightly different question of it than anyone had thought to ask before. Voyager 1's persistent hum sat quietly in the spacecraft's data for years, before anyone specifically went looking for it during the quiet stretches between solar events. That it took a dedicated, patient reanalysis to finally notice is a genuine reminder that even data gathered by hardware built in the 1970s can still hold discoveries nobody has gotten around to finding yet. If space discovery stories like this one, grounded in real published research from Nature Astronomy, and the scientists actually studying this data, are what you want more of, subscribe to this channel and turn on notifications, because Voyager 1 is still out there right now, still transmitting, and there's a real chance researchers are still finding new patterns buried in decades of data this spacecraft has already sent home. Thanks for watching, and I'll see you in the next one.